Hello and welcome back. Now we start to move towards some more complex code. And indeed, so far, all the code we have dealt with so far was such that we have all functionality either within our Python file or within the Jupyter notebook. So that's great that we have everything in one place, but clearly it doesn't scale for more complex tasks. And because as soon as we have more complex code, for example, notebooks become very long, it also becomes harder and harder to keep track of where we have defined things, and it also limits our reusability of the code. We would have to copy and paste things, and once we find a bug, we have to fit it everywhere, or rather forget to fix it in some place or other. Instead, Python supports modules, which are essentially files ending in py, and they're basically normal Python file, and they can hold functions, classes, generators, decorators, and so on, and then we can use and reuse these in many other pieces of code or even in Jupyter notebooks. And this is also one of the key benefits of using Python, because Python offers a very rich ecosystem with many modules and libraries that span a very large range of applications. It's also part of the best practices, which is called code refactoring. Whenever we have developed a useful function or a class or something, it is a good practice to put this into a separate file. This allows us to use it more widely, it's easier to debug, and it keeps our code simple and clutter-free. It also makes it easier to clean up our code and make it more readable, because we only sort of plug and play together what we need at the time. This is really the zen of code refactoring, improving and cleaning up code without adding new functionality. And any good software developer would spend considerable time of doing this. It doesn't have maybe the immediate benefit for the next 10 minutes, but it clearly adds to having well-maintainable code for the future. Now, once we have defined a module, that really means put the functions and classes, etc. into a file, we can make this usable in our own code with the import statement. But this can be done in multiple ways. So say we have refactored our code and put it into a file with the name myModule. Then we can do import myModule. This makes all functions and classes available in our current code. And to access this, we need to prepend myModule whenever we want to use it. We can also change the namespace and say import myModule as m, so we don't have to type myModule all the time, but just use m. This is indicated by the keyword as. Or we can import specific functions. From myModule, import my special function, myfunc. This makes sense if you only need one or two functions in the code we have at the moment. And that helps sort of reducing the prone of errors. There's also a bad practice, an anti-pattern. Quite often you see the following: from myModule import star, where star means everything. That has the disadvantage that now everything is available that was in this module. It does have the advantage that we don't need to write myModule or something beforehand, but now we no longer trace where this comes from. Imagine we have the situation where we import several modules, myModule 1, myModule 2, myModule 3, and then import star everything from everywhere. Then it would be very difficult to understand if something goes wrong, which function was actually called when. So, as an example, suppose we have moved the code that computes a Fibonacci series into a module called Fibonacci py. So we've done this in this tutorial as well. So here's the function, def compute Fibonacci with the numbers, and this is implemented using a list. So suppose we have this, and this is a separate function. Now we can use it in our code. We can say import Fibonacci, or if we don't want to write so much, we can import Fibonacci as fib. Or we can import the specific function. In our example here, we only have one, but we could have a long list of functions in here that are related to Fibonacci in some way. So let's use the second option. Import Fibonacci as fib. Now we don't need to code the Fibonacci series in this notebook here, but we use the code that is in this file. And we use the Fibonacci nummies are fib because we changed the namespace here, dot, and then compute Fibonacci, which is in that file. And then we use the print statement as before. And as before, the numbers are the Fibonacci series. Now, as we said before, in Python there are a lot of modules, and you will come in contact with a lot of them. In fact, if you can look at the Python package index, and at the moment there are more than 400,000 projects that you can import and use for your own purposes. And they span the range of scientific computing, machine learning, deep learning, statistical analysis, visualization of data, image processing, language processing, web development, databases, and many, many more. As a data scientist, the most generic and typical toolbed includes at least the following libraries. NumPy is an efficient library for computing on large multidimensional matrices or arrays, and also contains a large collection of higher-level mathematical functions. Pandas is a very powerful toolkit to analyze and handle structured data, so everything that can be contained in tables as well as time series data. Matplotlib and Seaborn are visualization libraries, where Seaborn is an extension that is built on top of Matplotlib and extends its functionality and provides a more intuitive user interface maybe. Scikit-learn is a general machine learning library, so like clustering, regression, classification with the classical machine learning libraries. And for PyTorch and TensorFlow, these are deep learning and neural networks libraries that are developed either by Facebook or Meta for PyTorch or Google Alphabet for TensorFlow. Each of them has a rich open source community with many specialized packages that augment these two and then add specific functionalities. Now let's take a closer look at NumPy, which is most frequently used for us for common mathematical functions like trigonometric, exponential, logarithms, and so on, common statistical functions like mean or variance, and in particular matrix and array operations. This is particularly important when we move to machine learning and deep learning, and this is really the foundation of storing and manipulating data in a wide range of libraries that are built on top of this. So NumPy is really heavily optimized for efficient and fast data handling, bulk operations, and you can often gain significant speed boost by implementing operations using NumPy compared to trying to build it yourself. So it's worth, when you do scientific computing, to first become somewhat familiar with NumPy and then use it to sort of offload compilation to it. We typically include NumPy like this in our code, import NumPy as NP. Of course, NP is an arbitrary abbreviation, but more or less everyone uses this. So whenever you see in code with NP, that almost always means that it's a NumPy functionality. The most fundamental data type in NumPy is an array, which can have one or more dimensions. And the rank is the number of dimensions, and these are called axes in the NumPy language. And the shape finds the size of the subarrays in each dimension. For example, we start with a one-dimensional array that we initialize with a list of integers. So we import NumPy and have an array, MP array, and then 1, 2, 3, 4, 5. So we have this array with rank, the number of dimensions, and shape. Notice here that we use the format statement and now explicitly refer to the variables that we give in the format statement 0, 1, 2. So this is our array 1, 2, 3, 4, 5 with the rank, the number of dimensions 1, and shape 5. So in one dimension it's 5 elements long. You can also have a multi-dimensional array, and this is defined pretty much in the same way. Here we have 3 arrays, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? And so we have 2 dimensions, 0, 1, 2, and shape 3, 3. 3 by 3. We can also make it more complex by nesting arrays, right? So we can have an array here and that has arrays in the array. You can really make it arbitrarily complex, and that is reflected in the shape. Later on in deep learning, we will extend this functionality when we move to sort of called tensors, and they have complex shapes that really reflects the input. But here we see that there's now an additional dimension axis. We repeat the block 1, 2, 3, 4, 5, 6 3 times. 1, 2, 3, 4, 5, 6 3 times. right? So each time we have a matrix with 2 rows. And we can make this more and more complex as the new array. You can also reshape this into a different dimension, right? So for example, we could rearrange the numbers in the array. We know that the number of elements, the elements themselves do not change, right? We still have the same elements, but the way they are arranged in this matrix and submatrix are different. And that depends on what we need to do. You can also access subparts of it and do this similar to what we did with slicing earlier when we worked, for example, with lists and tuples. Now, as an exercise, print the subarray with negative numbers. Change the negative numbers to positive numbers, for example, using NumPy apps. Print the resulting array. So we start with this one, 1, 2, 3, 4, 5, 6. Then we have here the negative numbers and operate on this.